So do you hear me?
Okay, so we can begin our seminar. It's a pleasure to have Luca Baracco from Padova to speak this week, and the title of the talk is Closed Range of D-bar-B on q-convex manifolds.
So thank you for the introduction. So first of all, I want to thank the organizer for giving me the opportunity to give this talk. So what I'm going to talk about today is a closed range of D-bar-B on q-convex manifolds. So to begin with, let me recall some definitions. So let X be a complex manifold of dimension n, and let J be its complex structure. So J is a map defined on the tangent bundle, and locally in coordinates, it behaves like this, like the usual multiplication by I. So let M be a real submanifold of X. The complex tangent space of M at the point Z is the subspace TZM intersected with JTZM, and roughly speaking is the largest complex subspace contained in the tangent space to M. M is a CR manifold if TCM has a constant dimension, and the complex dimension of this bundle is the CR dimension of the manifold. We will say that a real submanifold M of dimension 2p-1 is a CR manifold of hypersurface type if the codimension of the complex tangent bundle is 1, the codimension in M. In this case, the CR dimension of M is p-1. An easy example, so suppose that omega is an open subset of X with a reasonably smooth boundary, then the boundary of this set is a CR manifold of hypersurface type, and indeed is an hypersurface in the usual sense. So we define the anti-holomorphic tangent bundle to M, like this is the set of anti-holomorphic vectors which are tangent to M, and similarly we defined the holomorphic tangent bundle to M, like this, and naturally these two spaces are related by conjugations. So we have that both T10 and T01 have a complex dimension p-1, and they are involutive. So we have the composition on the tangent bundle of M, like this. So the tangent bundle decomposes in 3 pieces, the holomorphic and the anti-holomorphic tangent bundles, and an additional direction, an additional one-dimensional bundle that I call N, which is also called the totally real direction. So in particular, if we want to describe locally Tm, we just have to choose p-1 holomorphic vector fields in T10M, L1, Lp-1, and to complete this system and to have a basis, we just add the conjugates of these holomorphic vector fields, and we just need to add an extra direction that I call T, which is just a vector field not in TCM. And this is called a totally real direction of M. So in our normalization, we shall choose T to be imaginary with purely imaginary coefficients, so that T bar is minus T. And also, if M is orientable, we can choose a global T, which a global T once for all points of on the whole M. So let omega 1, omega p-1, omega 1 bar, omega p-1 bar gamma be a dual basis of this one. Now we define the Levy form of M with respect to gamma at a point Z as the following Hermitian form. So for any couple of vectors x and y in T10M at Z, we define the Levy form of M with respect to gamma as the contraction of gamma with the brackets of these two vectors. Here I denoted x tilde y tilde to vector fields in T10M that extends x and y. So we say that M is pseudo-convex at Z with respect to gamma if the Levy form of M with respect to gamma at Z is positive, semi-definite, and we will say that M is pseudo-convex oriented if M is orientable, and if we can choose a global T, and consequently a gamma, such that the Levy form of M with respect to gamma is positive semi-definite for all Z in M. So let BS be the let BS be the bundle of skew-symmetric S forms on T01M, and let C infinity S be the smooth sections of BS. Now, since T01M is involutive, the RAM-D complex restricts naturally to C infinity SM, and we call such restriction D bar B. So we have a complex like this, where C0 infinity M are the zero forms, which means smooth functions, and C infinity S is the set of all forms that can be written in this way. So it's a summation over all the multi-indexes J. J is a multi-index with the S slots, and its components are J1, Js. And Fj are smooth functions on M. Now, in degree 0, the kernel of D bar B is just the set of smooth CR functions on M, which are functions that annihilates the anti-holomorphic tangent vector fields to M. So we will call, we will say that an S form is D bar B closed if D bar B of F is 0, and we will say that F is D bar B exact if we can find an S-1 form U such that D bar B of U is equal to F. Now, many problems in CR geometry reduce in solving a D bar B problem, and the right setting for solving or for studying the D bar B system is the L2 setting. So, So now, to extend to L2 what I said, suppose that the ambient manifold X is endowed with an Hermitian product, and consider the induced product on M. So if omega 1 bar omega p minus 1 bar is an orthonormal frame of T star 01 M, we extend the scalar product to forms of higher degree by declaring that omega j bar is an orthonormal basis. And for two forms F and G, like this, we defined the pointwise scalar product between F and G in this way, and we define the scalar product of F and G with this integral, where dVm is the volume form induced on M. So the space L2S M is the space of S forms with measurable coefficients such that this integral here is finite. So L2S naturally is a Hilbert space, And we consider the maximal L2 closed extension of the bar B. And we have that this extension that we call again the bar B is a closed densely defined operator from its domain, which is a dense subset of L2M with values in L2S plus 1. And again, we have a complex. Also, we will need to consider the L2 adjoint of the bar B, which is just the usual joint in the Hilbert space sense and is defined by this relation. Also, I will need to put to consider the slightly different scalar product. So if phi is a smooth real function defined in a neighborhood of M, we define the weighted L2 space with weight phi in the following way. So it's basically almost the same product. The only difference is the addition of a factor here, the weight, E minus phi. So when the weight is present, I will put a small index to recall this, like here to indicate the norm. And also when I consider the L2 adjoint with respect to this product, I will add an index with the weight. When the weight is of the form T phi, for where phi is a fixed function and T is a parameter that I will need to modify, then I will just add T on the scalar product and on the adjoint of the bar. So we say that the bar B has closed range on a certain degree S if the range of this map is closed in L2. Now, closed range is an important condition because it underlies all the result on existence and the regularity of solution of the bar B. And the first result on closed range of the bar B goes back to Kohn and Rossi in '65, where they proved that if M is the compact, strictly pseudo-convex boundary of a domain in Cn, then the bar B has closed range. Now, for general pseudo-convex boundaries of domains in Cn, show and both show proved closed range on degree n-3 and degree n-2. And finally, Kohn in '86 proved that the bar B is closed ranged in all other degrees. But in the work of Kohn, there is much more. He proved that if M is the pseudo-convex boundary of a domain omega in a manifold X, such that there exists a smooth, strictly polarisubharmonic function phi in a neighborhood of M, then the range of the bar B is closed. Now, recall that to prove the closed range on a certain degree is equivalent to prove that given a form alpha of type d bar B U, we can find V, an S-1 form, such that the bar B of V is equal to alpha and V satisfies an estimate like this. Now, Kohn's idea consists in two steps. First, to extend in a suitable way alpha from M to omega to a d bar closed form on omega bar, and then to take the weighted canonical solution V of this d bar problem. And then by using microlocal analysis to prove that V gives 1/2 in regularity. And so when we take the restriction to M, we have that V satisfy the required estimate. So basically what is important is that M is the boundary of a complex manifold. So if we have
May I ask a question?
Yeah.
About the one-half gain in regularity, does this require any assumption on the domain, or is this the weighted canonical solution that gives this regularity?
Well, it depends on the domain and also on the particular problem that you choose to solve. So you have some freedom when you choose the extension of alpha from m to omega, but you choose very carefully the extension. So so it's a combination of the two things.
Okay, thank you.
So let's take let M be a compact oriented CR manifold of hypersurface type in Cn. This kind of manifolds are also called maximally complex. Then a classical result by Harvey and Lawson say that M is the boundary in the sense of currents of an analytic variety E. So this is not enough. We cannot use a cone strategy yet because we need M to be the boundary of a manifold in the smooth sense, and E in general is not smooth. But if we add some condition on M, we have that, and this was already proved by Harvey and Lawson, that if M is a compact, strictly pseudo-convex CR manifold, which means that the Levy form is positive, definite, then M is the boundary of the Harvey-Lawson variety in the smooth sense. And the same is true if M is pseudo-convex oriented and of finite type. So I would like to give a proof of this fact because I will need it later. So let Z be a point of M. We consider this complex P-plane Tzm plus JTZM, and we take the orthogonal projection pi to this p-dimensional space. Then we have that pi restricted to M is a diffeomorphism, and pi of M is a real hypersurface in CP. Now, since M and pi of M have the same CR dimension, we have that pi restricted to M is a CR diffeomorphism, which means that the inverse of pi is a CR map too. Now, if M is strictly pseudo-convex or of finite type, we have that pi of M enjoys the same property. Therefore, for every point on pi of M, we have a forced extension of CR functions, which means that for any point on pi of M, there exists two neighborhoods, U and V in CP of pi of Z, such that U is divided in two components, U plus and U minus. U minus is pseudo-convex, such that for every CR function on V intersected with the pi of M, any such f extends to a holomorphic function f tilde on U minus and smoothly up to the boundary, at least CK. So we apply this fact to pi minus 1. So we have that pi minus 1 extends holomorphically to U minus, and we have that the image of U minus is a complex manifold of dimension P whose boundary is contained in M. So let me draw a picture. So here we have M, our point Z. We take the projection on TZM plus JTZM. Pi of M is an hypersurface in CP. Here we have the pseudo-convex side of pi of M, and we have that pi minus 1 extends holomorphically on U minus, and the image of this half space here in CP is a complex manifold of dimension p whose boundary is, well, the image of pi of m, which is m. So we repeat this construction for all z in M. So we have many small pieces of complex manifolds attached to M. They all glue together and they form a collar-like manifold Y, whose boundary contains M. Well, note also that the side of extension is always the same, always the pseudo-convex side of M. So when we put all these pieces together, we have something like this. And the fact that all these pieces lies on the same side can be said also in this way. The totally real direction T always point inside our manifold Y. Okay, so the manifold Y looks like this. The boundary has two components. One is M, and another one that I call M2 is diffeomorphic to M. And but we need M to be the only part of the boundary of the complex manifold that we are looking for. So we need to fill this hole here, and the natural candidate to fill this hole is the Harvey-Lawson variety. Now we have that Y, the color that I just showed you, is contained in E, and these two sets, they coincide at the regular points of E. Now, by a desingularization argument, there exists a complex manifold, E tilde, and a proper bimeromorphic map from E tilde to E, which is a real bilomorphism at regular points of E. Now, the singular set of E is an analytic set of lower dimension. So on an open dense subset of Y, we have that chi is a bilomorphism. So since both E tilde and Y are manifolds, there is a copy of Y inside E tilde, and the boundary of E tilde is CR diffeomorphic to M. And so we get the conclusion. Now, this construction can be done also when M is merely pseudo-convex. In fact, we have, if M is a compact pseudo-convex oriented CR manifold of hypersurface type of dimension 2p minus 1, then the bar B have closed range. Now, for p greater than 2, this was proved also by Nikohara in 2006 using different methods. So, how do we prove it? So we prove that M is the boundary of a complex manifold. So we recall that if M is a real hypersurface in a complex manifold, and Z is a point of M, then we have this alternative. So either there exists a germ of a complex hypersurface, H of Z, contained in M through Z, or every germ of CR function on M at Z extend holomorphically to one side of M, and the side is the same for all germs. So at points where we have automatic extension, we can repeat the construction above. And also, we are sure that the side of extension given by TREPRO is always the pseudo-convex side. And since M is pseudo-convex oriented, we are sure that the side is always the same. So the only problem is represented by the points which are not points of automatic extensions, points where there is a complex hypersurface, a complex leaf of dimension p-1 contained in M. But luckily, complex manifolds are propagator of holomorphic extension. So the idea is that at points where we don't have automatic extension, we propagate extension from other points. So let me show you another picture. So this is our manifold M. This is a bed point Z, a point where we don't have automatic extension. So there is a complex manifold of maximal dimension passing through Z. And where this manifold ends, where it is not possible to continue it inside M, means that the final point of HZ is a point of automatic extension, and using Hangers and Treves, we propagated the extension here to the point at Z. So the proof is complete if we can prove that every complex leaf in M ends at point of automatic extension. And this will be proved in the following slides. So to prove it, I need the notion of global minimality. So let M be a smooth CR manifold and Z a point on M. The CR orbit of Z in M is the union of all piecewise C1 integral curves of TCM issued from Z. We say that M is globally minimal if M is a single CR orbit. We also define the local CR orbit of point Z, and we indicate it with like this, and is the union of all piecewise C1 integral curves of TCM which are contained in a neighborhood of Z. So we have that the local orbit is locally is a manifold. So if M is of hypersurface type, this means that the local orbit of a point is either an open neighborhood of Z or a complex manifold of dimension p-1. So what I want to prove is that if M is a smooth, compact, connected CR manifold of hypersurface type in Cn, then M is globally minimal. So this is how this is the proof. So let A be the smallest non-empty closed CR invariant subset of M. CR invariant means that it is invariant under the action of the flow of any CR vector field. So let Z be a point in A. Then we consider the orbit, the CR orbit of Z, which is, we have the two possibilities. So either the orbit of Z is a complex hypersurface or is an open neighborhood of Z. If the orbit is open, then by the minimality, in the sense of set inclusions of A, we have that the orbit must coincide with M. You just consider A minus the orbit, you get again a closed invariant, a CR invariant subset. And since A is minimal, we have that it must be empty. So the orbit of Z must be equal to A, but the orbit is open and A is closed. So since M is connected, the orbit must coincide with M. So we are done. So suppose that this is not the case, that for any point in A, the orbit is a complex hypersurface. Then A is foliated by a complex leaf of dimension p-1. And this is gives a contradiction because let phi be a strictly plus harmonic function defined in a neighborhood of M. we are in Cn, so we can take, for instance, modulus of z squared. Then we have a contradiction, because by the maximum principle, we take the point where phi reaches its maximum on A, let me call it z naught. So there is a complex leaf of dimension p minus 1 passing through z naught, and if we take the restriction of phi to h z naught, we have the contradiction, because we have a point of maximum, and phi is Plary-subharmonic, and is strictly Plary-subharmonic, and it cannot be. Okay, so this shows that every p minus 1 complex leaf inside M must end at point of automatic of forced extension. In fact, we do have point of automatic extension on M. For instance, take the point where phi reaches its maximum on N. Then, as we just proved that there cannot be any complex leaf through Z naught, so that is a point of automatic extendibility. And suppose you have a leaf, a complex leaf that never ends, then we have that this leaf must be equal to the CR orbit of Z, which in turn is equal to the CR orbit of Z naught, and this is impossible because there are no complex leaf through Z naught. This completes the proof. So now we change the environment and consider the q-convex case. So let me recall a couple of definitions. So let U be an open subset of Cn. A function phi from U to R is q-convex if the Levy form, which is the complexation of phi, has q-positive eigenvalues. We say that a complex manifold X is completely q-convex if there exists a smooth q+1 convex exhaustions phi on X. So with these definitions, we have that Stein manifolds are completely n-1 convex. So we have this theorem. So let M be a smooth pseudo-convex oriented compact CR submanifold of X of dimension to p-1, and assume that there exists a smooth q+1 convex function phi defined in a neighborhood of M in X. Then the bar B has a closed range if S is between n minus q and p plus q minus n, and P is larger than 2n minus q. Moreover, if we assume that X is completely q-convex, the same conclusion holds for P equal to 2n minus q.
Excuse me, Luca, I think there is a question.
Yes?
Adriano, you have a question? Well, maybe I'm wrong. Sorry, please go ahead.
So,
Adriano, sono domande?
No, non so cos'era, forse si è azionato la mano, ma non l'ho fatto inavvertitamente.
Okay, no problem. Go ahead, Luca, scusa, sorry.
Okay, so, so we want to follow the technique of Kohn. So first we want to construct a complex manifold whose boundary contains M. So the construction of the color like in the Cn case can be done also in this case. The only difference is that when we prove the global minimality of M, we need P larger than n minus q. So in fact, if Hz is a complex leaf of dimension p-1, we need the Levy form of phi restricted to Hz to have at least a positive direction. Now we know that number of positive eigenvalues of phi is at least q plus 1. So when we take the restriction to hz, which has dimension p minus 1, we can expect to have at least q plus 1 minus the codimension of hz, which is n minus p plus 1. And we want this to be positive, and so we have that p has to be larger than n minus q. So we have a color manifold around M. So if X is Q complete, we have an equivalent version of the Harvey-Lawson theorem. So there exists an analytic set E whose boundary in the sense of occurrence is M. Again, we have that Y is contained in E, and they coincide on the regular part of E. So we can find the desingularization E tilde, a complex manifold E tilde, which desingularize E, and we have a copy of Y inside E tilde. So then we restrict our function phi to E tilde. We pull back phi to E tilde. And so we have a function which has whose number of positive Lebesgue eigenvalue is at least p plus q minus n plus 1. Now, to go through with the Cohn's proof, we need an estimate of this kind. So it is enough to prove it locally near the boundary of E tilde, that is M. So let Z be a point on M, and let UZ be a neighborhood of Z in E tilde, and let L1, LP be a normal frame near Z. So L1, LP minus 1 are complex tangential to M, and LP is the extra missing direction. So we exploit the Cohn-Maurer-Ormander formula, and we have this inequality. Also here there should be a boundary, an integral, involving the Levy form of M, but since M is pseudo-convex, it is positive, so I already dropped it from this inequality. And lambda jk is the Levy form of phi restricted to E tilde. Now, as I said, this form has at most n minus q minus 1 non-positive eigenvalues. And so the second term here, which is the useful one, is will be positive on forms of degree greater than n minus q. So to end, to prove that we have a closed range on degree s minus 1, we need this estimate in degree s and p minus s plus 1. So we have that S has to be between these two numbers, and so this proves the case when X is completely q-convex. If X is not completely q-convex, then we cannot fill the hole of the color, but still we can manage to have an estimate like this following the work of Shaw in 85. The main difference is that Y has the boundary of Y has two components. One is M, which is pseudo-convex, and the other, which looks like the opposite. So when we exploited the Cohn-Maurer-Ormander formula, we have a boundary integral whose sign is not very is the opposite of the one of M, and to control that we need to take advantage of this term here and to perform some integration by parts. So in the process, we unfortunately lose a degree, and we have the conclusion only for p larger than 2n minus q. So I stop here. Thank you.
Thank you. Thank you very much. I'd like to ask if there are any questions.
I have a question.
Okay.
Please go ahead, Alberto.
Okay. Luca, you said about your theorem of 2012 about you have a CR manifold which is of hypersurface type of dimension 2p minus 1, which is convex and pseudo-convex, and then you get the d bar b as a closed range. I would like to ask you if the compactness hypothesis has some other need you need for something else, or just to apply Harvey-Lawson?
Well, I needed to apply Harvey-Lawson and also to prove the global minimality of M.
Okay, yeah. I asked you this because me and Giuseppe Della Sala in 2007 generalized a little bit Harvey-Lawson, dropping the compactness hypothesis. So if compactness wouldn't be needed elsewhere, then you can remove compactness and ask that just that the pseudo-convex manifold is not big at infinity, meaning that it does not take all direction of the line at infinity when you take the closure in CP1. So if you don't need the compactness elsewhere, maybe there is a way to apply Harvey-Lawson also without that hypothesis.
It is needed, definitely.
Okay.
Yeah.
I think we have another question. Sorin, you should open your microphone.
Ok.
Ciao Sorin.
Ciao, buonasera a tutti. So my question is just a curiosity about the same theorem which was mentioned before. Could you perhaps put back that slide where you have a CR submanifold of real hypersurface type, and then the conclusion is that the d bar b operator has closed range?
Okay. This one?
Yes, that's the one. I think I'm missing something, because it looks like the theorem doesn't apply to the Rossi sphere. You know, the three-dimensional sphere endowed with what we call the Rossi CR structure, which is actually discovered by Cartan, but we call it Rossi structure. So we know that is not embeddable in C2, but
it doesn't have a closed range, right? Yes.
And it satisfies all assumptions, and d bar b doesn't have closed range.
Yeah, but here we are talking about embedded manifolds in CN. So the complex structure is the standard one. Rossi example, it doesn't have the standard complex structure.
It does have the structure induced by C3. There is an embedding of M in C3, and that induces precisely the Rossi CR structure.
A CR embedding in C3?
Yes. You can find it, for instance, in an old paper by Daniel Burns.
So you're talking about for me, the Rossi example is where the CR structure is given by L plus epsilon L bar, right?
Okay, that's the one.
That's the
and
one.
you can write an explicit CR embedding of that into C3, which is proof is rather easy. You use
and the image is a
harmonic compositions.
And the image is a CR manifold?
Certainly.
But so it's in embedding, but is it an embedding? Because all CR functions on the Rossi example must be even, right?
Yes, that's true.
So
Certainly.
the image that you get on the other side is no longer diffeomorphic to the sphere, right? So it's
if you think of the ordinary embedding of M in C2,
but also in C3, because opposite points ends in the same point, right?
You don't have a global embedding there, but you do have a global embedding in C3.
So, but the image is no longer what it is like so maybe you lose the orientability.
What do you mean? That's an intrinsic property of the manifold. I mean, it's the sphere is orientable.
So I don't know. I need to have a closer look to.
Yeah, maybe the step out of this problem is that you don't have you don't have a global statement about the tangential Cauchy-Riemann operator having closed range. You must have only some local statement. That might be true.
No, it is a global one, and
oh, it doesn't apply to the sphere. But anyways, that was the question.
Excuse me,
I don't know.
May I make a comment? Isn't it true that the CR functions, as Luca Baracco said, are even automatically? How could it embed injectively in an
ECN? Cannot embed injectively in C2.
Okay. Not even in C3, right? Because
no, right.
So I think the theorem is about embedded things. I think. Yeah.
Okay. All right. Yeah. Are there do we want to add anything to this, or are there any other questions? Well, Luca, unless you want to add anything, I guess we can ask Luca again. And